Good morning. This is Michael Dong on video number 24, Food Testing by HPLC, a primer. Here's a summary on the topic. Many of the detections are using ultraviolet, fluorescence, CAD, and mass spec detection. The perspective of HPLC in food testing is used in product research, QC, and also nutritional labeling, plus the analysis of contaminants. I'd like to characterize the food testing into three different categories. First is natural components. Second is food additives. The third is trace contaminants. Like before, HPLC have several advantages such as resolution, multi-component analysis, quantitation analysis of both the main component and traced contaminant or components, and also provide very optimum sensitivity and specificity using different detectors and different columns under different operating conditions. There's an increasing trend of using UHPLC for high resolution and speed, supercritical chromatography, ELSD, which is light evaporative scattering detector, or CAD. CAD stands for charge aerosol detector. CAD probably is preferred for most people for non-chromophoric detector, so you can get away from refractive index detector. And obviously, the increasing use of LC mass spec, particularly triple quad or high-resolution mass spec such as TOF. Another big trend is the use of KERSHA, which we will explain later, the acronym for quick sample extraction and easy and cheap separation for sample prep. For nutritional labeling requirement, they're typically done for energy content, macronutrient, micronutrients, serving size, and daily value. Some of the mandatory nutrients can be assayed by HPLC, such as sugar, a different type of sugar, and also micronutrients such as some vitamins. Here is a summary of the different HPLC mode and also detection. Some of the acronyms such as HILIC, standing hydrophilic interaction chromatography, NARP or non-aqueous reverse rate are shown here, some of the detection. So once again, three different category, natural components, food additive with all the different HPLC mode and detection options, and also contaminants increasingly being done by triple quad. A summary on natural food components focusing on sugar. Sugar obviously is a common carbohydrate. Most are monosaccharides such as glucose and fructose. Could be disaccharide such as sucrose, maltose, lactose, and triglycerides, and polysaccharide in terms of starch. Now, HPLC offers traditionally a very robust quantitative methodology, and we will describe that in much later, using a mixed mode cationic resin-based column with refractive index detection under isocratic condition. You can also increase the sensitivity and separation power by using under grading condition using a CAD detector. The resin of choice is the one with the counter ion, calcium ion. The basis of separation and retention mode is a mixed mode mechanism, which include a mode containing size exclusion, ion exclusion, ligand exchange, and also hydrophobic interaction with the polystyrene resin support. The reliability is excellent and proven over time. Here is an application which is performed quite a while ago, showing the separation of a simple sugar in soft drink with a sample of Coca-Cola, using a calcium-based resin column, using just water as the mobile phase at a pretty high temperature of 85 degrees, using a refractive index detector, separation of the 5 simple sugar. Now, in America, Coca-Cola is sweetened by high fructose corn syrup because it is inexpensive and is very sweet. So this assay is very robust. Here's an example of some modernized version of sugar analysis using a single quad mass spec and detection using a single ion reaction, a single ion monitoring, showing that this application is from Waters Corporation. So the separation is mode using helic or hydrophilic interaction chromatography. Next one is natural food component of fats, oil, and triglyceride. Fats and oil are triesters of glycerol, modified with bonded to different fatty acid, called triglyceride. Fatty acids are commonly analyzed using gas chromatography as their methyl ester after sample transesterification. However, HPLC often can play a role in certain applications. Edible oil can also be injected directly using a reverse phase called non-aqueous reverse phase, as shown later. Other fat components are phospholipids and common steroids such as cholesterols. This is a very old application published in 1983 in Journal American Oil Chemistry, an ACS publication, showing the analysis of triglycerides in olive oil. At that time, is one of the most highest resolution achieved on that time. So if you inject a sample olive oil obviously is not just a single component, it's a family of components with the major being an oleic acid, it's monosaturated acid. So OOO, designating the 3 oleic acid in the chain, is the major component. So you have these distinctive profile using this condition. The reason why it's called non-aqueous reverse phase is the fact that you do not use any aqueous mobile phase because the oil is really hydrophobic, right? So you actually use something even stronger than acetonitrile, which is acetone. And this under using refractive index detection under isocratic conditions. Just a note that most olive oil in the market may be misbranded, or a lot of them are fake because one can garnish very high prices for olive oil. So this is a technique to counter counterfeits goods. Here is a modernized version of same separation mode, but under a grading condition. You cannot use refractive index detector, so the detection of choice is CAD. You can also ID it by mass spectrometry. Here is the separation of cholesterol using silica under normal phase conditions. Continuing on the natural food component, we are getting into the area of free fatty acid and also organic acid. Once we mentioned that the free fatty acid can be analyzed under reverse phase condition with low UV detection at 210. We show some example. Also, you can use various column derytization with reagent shown here, even though that the main assay technique is using GC of the methyl esters. Organic acid is a much responsible for the organoleptic property of foodstuffs such as wine, and there are different type of organic acid shown here, and we will show example on the assay of organic acid in wines. So quick application on undirectized long-chain fatty acid using low UV detection at 220. We were using a 0.1% phosphoric acid, which is transparent under these conditions. So here's a mixture of separation of fatty acid standards. This was done also quite a while ago using a derivatized fatty acid analyzed by finger oil sample using UV detection under derivatization. The derivatization technique is using a para-bromophenol ester of the fatty acid, showing pretty high sensitivity and really good separation under grading condition. Organic acid organoleptic component responsible for flavor of wines and other foodstuffs. So it's, the assay is of great interest for food quality, particularly in wine. So we did a publication in the late 1990s on HPLC assay organic acid. So this is a good white paper on the topic. So shown here is the use of, once again, a resin column, but this time not as a calcium counter ion form, but is with hydrogen as the counter ion. Shown here is a standard of the organic acid, and one can use either refractive index detection or low UV detection. Shown here is detection using refractive index detector. And here's a sample of grape must, after harvest of the grapes before fermentation, and a white wine sample showing levels, quantifiable levels of organic acids in wines, in white wines. Next is a classification of food proteins. Shown here are various cereal proteins from albumin, globulin, and also milk proteins such as casein. So total protein is commonly estimated or analyzed by Kaldal method, which is using acid digestion, which released ammonia being titrated by acid-base titration. However, HPLC can furnish definitely more about the actual speciation of protein and the protein profile information. So protein can be separated very much like biopharmaceutical using different mode of HPLC, including ion exchange, size exclusion, reverse phase, and others. An example of proteins in egg whites showing lysozyme and also O-valbumin using a very specific C18 column, which is using trifunctional silane chemistry to give more size selectivity. The analysis of amino acid, because of the fact that it is very highly water soluble, so you cannot use reverse phase, and also it is most of them are not chromophoric, so you have to do some type of derivatization. So amino acid analysis is useful for assessment of nutritional value of food and feedstuff, difficult to analyze because they are highly water soluble, not compatible to reverse phase, and non-chromophilic. And essential amino acids are listed here. Several of them have a chromophore in UV. Note that glutamic acid is a commercial flavor enhancer. So typically two types of amino acid analyzer, which we discussed in earlier videos. One is post-column derivatization using the anhydride post-column reaction, or OPA, mostly in anhydride. The other one is pre-column derivatization. So an example of ion exchange chromatography followed by post-column anhydride derivatization under high temperature, showing the separation. The chromatograph actually was furnished by Pickering Laboratory, which make a post-column derivatization module, which can be added to any HPLCs. So here is the separation of the essential amino acids using sodium cationic exchange, using 3 different buffers with different pH from 2.7 to 7.4. One can get higher sensitivity by using pre-column derivatization. One of the best reagent, you can use many reagents. One of the best one probably will be the one developed by Waters Corporation, which actually make a kit called Acutech with column reagent and a workbook to help the analysts do pre-column derivatization. The next big area is food additive. These are the different category from acidulants to sweeteners, such as aspartame, saccharin, sucrose, which is splendor, and other favorite component, which give you bitter, pungent, and aromatic compounds. And also additives such as antioxidant and preservative, and color and food dyes, and also water-soluble and fat-soluble vitamins. An application on the sweetener, flavor, and preservative in soda. So here's an application done a while ago of cream soda, which contain 5 components, easily assayed under isocratic conditions, under ion pairing reagent conditions. And those are saccharin, caffeine, aspartame, which is a sweetener, vanilla, the flavor, and sodium benzoate as a preservative. The assay of the heat level in pepper, which are caused by a class of compound called capsaicins, is of interest for manufacture of hot sauces or different kind of pepper. Typically, the hotness of the peppers being assayed by a taste panel and being rated on the Scoville value test. However, those are expensive and can be substituted by an HPLC assay. So I published a interesting paper on the measurement of the heat level of different pepper or hot sauces using the HPLC separation of different capsaicin. Because the heat level are different, you can basically assay them and summarizing using a program with the chromatography data system actually give you the Scoville level within an hour of the sample prep plus the assay. So this is of interest to some of the manufacturers. The bitter components such as the commercial hop extracts are shown here in application. Next is also some flavonol and phenolic acid extracted from beers. Next category is food category. Showing here is an application from Agilent technology from Germany, from Warbram, on fast UHPLC separation of different preservatives. Next is another application on the phenolic antioxidant in food with an application example of an extract of chicken flavor bouillon. These are done quite a while ago under grading conditions. The application of preservative in dog food extract are shown here. Some of the pretty common preservative are ethyl paraben, propylparaben, sorbic acid, also hydroxyl benzoic acids. The HPLC analysis of dyes, food dyes, kind of in the news these days from the banning of the recent banning of a number of dyes, synthetic dyes, as being phased out, and some of them being phased out being shown here. These are underlined and labeled in red. So I did this application a while back, showing the quick separation in the fast LC condition of 12 FD&C food dyes. So at that time, all these were allowable, but today several of them are shown to have some biologic activity and being in the process being banned. The detection wavelength for all the dyes actually is at 290 because it's a common wavelength, allow you to detect all type of dye. And you can make it very specific by tuning your detector to the visible region. It's better to have a detector which have a tungsten lamp to give you high sensitivity if those are important. Once again, another application published on the HPLC analysis water-soluble vitamin using ion pairing application. And at that time, the column was modified with adding TEA to suppress the selenophilic activity. So today, obviously, there are better columns being made, and you don't need this type of masking agents just have triethylamine to suppress it. But anyway, so that was developed in support of a multivitamin analysis system shown here. The summary of validation data was summarized in this big table here, showing very good performance HPLC. However, the weak part of multivitamin analysis is actually the sample extraction. It's very difficult to extract quantitatively, particularly from a multivitamin or multimineral tablet. That's definitely the weak part. The assay actually is much less, more robust and less variation. A newer rendition of water-soluble vitamin, this one is supplied by Agilent Technology from the Bangalore site in India, showing rapid analysis using a superficially porous column, the porous shell column, a very quick analysis in under 2 minutes of all the water-soluble vitamin. This one actually includes some vitamin B12. It's a very quick mention of analysis of vitamin E tocopherol, which can be done using a fluorescence detector under normal phase condition. It was described in the previous video for normal phase chromatography, which is good for the separation of isomers. A similar application of tocopherol showing more different components. Also, more recent publication with David Gamble, University of Geneva, in 2017 with myself on the UHPLC Part 3 on potential issues, demonstrating excellent high-resolution separation of some of the difficult to separate isomers, but being made possible by UHPLC with a longer columns. So a third category is contaminant. We're starting with some mycotoxin, which are toxin produced by moths. Some of these are regulated because they are highly toxic, such as aflatoxin in peanuts and grains, and there are other mycotoxins. Applications on aflatoxin in peanut extract, showing one can get a very high sensitivity down to ppb levels in extract using fluorescence. Antimicrobial antibiotic residue in animal product also can be assayed by HPLC quite readily using a set of column UV or fluorescent detections shown here. And this particular chapter in this book, which is kind of the go-to Bible on HPLC testing on food testing, are shown here, analysis by HPLC. So once again, an application from PerkinElmer application note on the separation of an antibiotic using this particular column using trifunctional silane chemistry. The HPLC analysis of pesticide in food is very important, and typically these multi-residue methods are using these Kokersher type of extraction. We explained that a little later, with HPLC separation, followed by triple quad quantification for trace analysis. So separation typically for foodstuff is extraction, such as homogenization, solvent extraction, cleanup by solid phase extraction, SPE. Derutinization may be needed in some cases. The modern trend is use something called the Kersher technique, which stands for quick, easy, cheap, effective, rugged, and safe. So these are typically SPE type of product for multi-residue LC triple quad procedures. So there's some common pesticide residues, herbicide, fungicides. One can also do separation or sample prep using GPC, shown here using a GPC sample prep separation to isolate the pesticide fractionation using GPC, getting away from high molecular weight oil fraction from fish oil. One example, we would describe that in the next video on environmental testing of carbamates using post-column OPA derutinization with fluorescence detection. Shown here is a spinach extract containing a pretty high level, above regulation level, of a certain carbamates in spinach. So here's a reference, and I would say that the one in red is the most important one, which is the Bible on food analysis by HPLC. On that note, we ended our session on the episode number 24, Food Testing by HPLC, a primer. You're encouraged to subscribe for future video and get notified on other one being in the channel. And we welcomed LCG CSA channel collaborator. We see you next time.